Welcome viewers. In this video we'll see the Biot-Savart's law, definition and derivation. The Biot-Savart's law mainly give the expression for magnetic field intensity. The expression for magnetic field intensity is given by the Biot-Savart's law. We'll see the definition. Steady current flowing through a straight conductor produces magnetic field in the form of concentric circles. When a current is flowing through a straight conductor, what will happen? The magnetic field is produced in the form of concentric circles. The intensity of this magnetic field is given by the Biot-Savart's law. The intensity of this magnetic field is given by this Biot-Savart's law. We'll see the diagram. So this is a straight conductor. The straight conductor is available. The current is flowing through this straight conductor. At point P, we are going to find what is the magnetic field intensity due to this straight conductor, straight current carrying conductor at point P, which is at a distance r meter. AR cap is the unit vector. This is the angle theta. This straight conductor is assumed to be having so many current elements. Current element is nothing but ideal vector. I into dl vector is a current element vector. There are so many current elements available. We consider one current element at this point. Further we can go for integration, right? So this is the straight current carrying conductor. Due to the current, the magnetic field is produced. We are going to find the magnetic field intensity at this point P due to this current carrying conductor, which is located at a distance r vector. AR vector is a unit vector along this. This is the angle theta. The straight current carrying conductor is assumed to be having so many current elements. Consider one current element ideal at this point. This unit vector can be expressed in two different ways. In terms of magnetic field intensity, the H is nothing but magnetic field intensity. DH means magnetic field intensity due to only small current element, only one current element. So the unit vector in terms of magnetic field intensity is given as dH vector divided by dH, vector by scalar, dH vector by dH. In terms of distance vector, it is r vector by r, vector by scalar, r vector by r. So the unit vector can be expressed in terms of magnetic field intensity or in terms of the distance vector. Now we'll see the definition. A straight conductor is assumed to be formed by several segments. Such a segment is called current element. There are so many segments available. That segment is nothing but current element. We consider the current element is nothing but ideal vector. The definition for current element is the ideal vector. Let the magnetic field intensity at point P due to the current element is dH. The H is the magnetic field intensity. dH means only due to one current element. So at point P, magnetic field intensity due to the current element is dH vector. By integrating, we'll get the total magnetic field intensity. Now we'll see the definition. According to Biot-Savart's law, what is the definition given? According to Biot-Savart's law, the magnetic of dH vector is proportional to ideal. Biot-Savart's law, the first statement given, this magnetic field intensity is directly proportional to current element, ideal, and inversely proportional to square of the distance between the element, that is r. Inversely proportional to square of the distance between the current element and field point, right? So it is directly proportional to ideal and inversely proportional to distance between the current element and field point, right? So that is given here. dH is directly proportional to ideal divided by r square, directly proportional to ideal, inversely proportional to r square, and also it is proportional to sin theta, sin of theta. So while equating, we need to introduce one constant, that is 1 divided by 4 pi. So dH equal to 1 divided by 4 pi ideal divided by r square into sine theta. So this is the expression from Biot-Savart's law, but this is the scalar. Scalar in this, it is in the form of scalar. Now we'll see what is the vector form. So in the vector form, we already discussed the unit vector. Unit vector AR is nothing but vector by scalar. From that, DH vector can be written as DH into AR vector, AR cap. Right? So the vector equal to scalar into unit vector. That already we discussed near the diagram. So this DH is nothing but scalar. So we can substitute from the previous equation. Ideal sine theta divided by 4 pi r square into AR vector. So this is in the form of now vector form, magnetic field intensity in vector form. So that can be rewritten as DH vector equal to ideal AR vector, AR cap into sine theta divided by 4 pi r square. Now refer this, A vector cross B vector equal to AB sine theta. A vector dot B vector is AB cos theta. A vector cross product means AB sin theta. Now consider this is ideal is the A vector. AR cap is the B vector. So what will happen? Ideal vector into A vector means ideal AR sin theta. So that is available here. So this ideal AR sin theta can be replaced as ideal vector cross AR vector, AR cap. Like similar this A vector cross B vector, right? So this is A, this is B, this is sin theta. So AB sin theta is can be written as A vector cross B vector. A vector, that's ideal vector cross AR cap divided by 4 pi r square, right? So based on that we wrote this expression. But unit vector, one more form is available, r vector by r. In terms of distance vector, it is r vector by r. So replace this AR cap as r vector divided by r, right? So already here one r square is available. So ideal vector cross r vector divided by 4 pi r cube. So this is the magnetic field intensity in the vector form. So by integrating on both the side, we will get the total magnetic field. So integral DH vector equal to integral ideal vector cross r vector divided by 4 pi r cube. So integral DH is h, that is equal to integral ideal vector cross r vector divided by 4 pi r cube. So this is the magnetic field intensity in the scalar form, in the vector form. The previous one, first what we discussed is the scalar form. So from the magnetic field intensity, we can find the magnetic flux density, B also. So there is a relation between B and H, B equal to mu H. So that B equal to mu into, the H is nothing but this value, integral ideal vector cross r vector divided by 4 pi r cube. So now we got the expression for magnetic flux density also, right? So the magnetic field intensity and magnetic flux density expressions are obtained from the Biot-Savart's law. So in this video, we discuss about the Biot-Savart's law, definition, derivation. Finally, we got the expression for magnetic field intensity and magnetic flux density, B for the expression. Thank you. Welcome viewers, in this video we will see the magnetic field intensity due to the finite conductor. the expression for magnetic field intensity due to the finite conductor. So our aim is to find the magnetic field intensity to a finite conductor, current carrying conductor at point P. The point P is at a distance d meter from the origin. Right? Now we'll refer the diagram so that it will be easier. So this AB is nothing but a finite conductor in which the current is flowing. When the current is flowing through the conductor AB, what will happen? The magnetic field is produced in the form of concentric circles. Right? AB is the state conductor in which the steady current is flowing. Due to that, the magnetic field is produced in the form of concentric circles. Our aim is to find the magnetic field intensity at this point P, which is at a distance d meter from the origin, or it may be center. Magnetic field intensity at point P, which is at a distance d meter from the origin. This fine conductor is assumed to be having so many current elements. Current element means ideal. Now we consider one current element IDX at this point. There are n number of current elements available, in which we are considering one current element IDX at a distance x meter from the origin. So this angle will be theta. There are n number of current element, in that we consider one current element IDX at a distance x meter. Further we can go for integration. So the angle between this point P and A is alpha, and point P and point B is beta. So AB is equivalent to in the angle of alpha and beta. The length AB, the equivalent angle will be alpha and beta. So for during the calculation we need this triangle. So this triangle is drawn separately. This distance is D, X and R. This will be angle theta. Now we'll see the description. A straight current carrying conductor AB assumed to be formed by several segments. Such a segment is called current element. Right? There are n number of segments available. That segment is nothing but current element. In that we consider one current element IDX at a distance x meter from the origin. We consider one current element. The distance between this current element and point P is R meter. So the dH is the magnetic field intensity at point P due to the current element IDX. The H is the magnetic field intensity. dH means magnetic field intensity due to only one small current element IDX. So by integration we will get the total magnetic field intensity. Right? So the dH is the magnetic field intensity due to current element IDX. Now we start with Biot-Savart's law. In order to find the magnetic field intensity expression, we start from Biot-Savart's law. dH vector equal to ideal vector cross R vector divided by 4 pi R cube. That is the expression given by Biot-Savart's law in the vector form. Ideal vector cross R vector divided by 4 pi R cube. Here we are using IDX. At a distance x meter we consider one current element. So that IDX into R vector divided by 4 pi R cube. What is A vector cross B vector? A vector cross B vector equal to AB sin theta. So that ideal vector cross R vector equal to IDX. IDX into R vector equal to IDX into R into sin theta. Right? So A vector cross B vector is written as AB sin theta. So here one R is there, here R's cube is there, so it become one R got cancelled. So that dH equal to, now this vector, this A vector cross B vector is written in AB sin theta in a scalar form. So now it becomes scalar. IDX sin theta divided by 4 pi R square. So after simplification, what we got? IDX sin theta divided by 4 pi R square. Now we have one triangle. From that we are going to find the expression for dx and r. From the triangle we are going to find the expression for dx and r. right? So this is equation number 1. So this triangle is available. This triangle I drawn again. D, this distance is D, X and R. We'll find the value of sin tan theta. Tan theta equal to, our aim is to find the value of X and R. So that first we'll find tan theta. Tan theta equal to opposite side by adjacent side. Opposite side is D, adjacent side is X. So D by X. Tan theta equal to D divided by X, right? So interchange these two values. X equal to D by tan theta, because what we need is X. So bring this X in the left hand side, tan theta in the denominator. So X equal to D by tan theta. 1 divided by tan theta is cot theta, right? So X equal to D cot theta. But what we need is dx. So we need to differentiate on both the sides. So dx equal to differentiation of d cot theta. So dx equal to minus d. So the differentiation of cot theta is cosecant square theta into d theta. So that we got minus. Right? Differentiation of cot theta is minus cosecant square theta d theta. So dx equal to minus d cosecant square theta d theta. Now find the expression for sin theta. Sin theta equal to opposite side by hypotenuse. D divided by r. Again cross multiply these two. Right? So r equal to d by sin theta. So r equal to d into cosecant theta. Now we got the expression for dx and r. We are going to substitute this dx and r in equation number 1. What is equation number 1? I dx sin theta divided by 4 pi r square. In this we are going to substitute this dx. Dx equal to minus. So I into dx is minus d cosecant square theta into d theta into sin theta is there divided by 4 pi r square. What is r? D cosecant theta. So d square cosecant square theta. Dx and r values are substituted. Right? Here 1d is available, here d square is available, so 1d got cancelled. Cosecant square theta available in numerator as well as denominator, that got cancelled. Now we'll see what is the simplified expression. So after simplification, what we have? Minus I by 4 pi d sin theta d theta. Minus I by 4 pi d sin theta into d theta. So this magnetic field intensity due to only one current element, small current element. By integrating on both the side, we will get the total magnetic field intensity. So the magnetic field intensity due to entire conductor can be obtained by integration. Then what is the limit for this integration? Current element has to move from B to A, right? From point B to point A. So the corresponding point B, we have the angle beta. For the corresponding the point A, we have angle alpha. So that beta to alpha, because integral is with respect to theta. If it is length, we can use this, but with respect to theta, so we are using the angles beta to alpha, right? So the limits are from beta to alpha. Now we'll substitute, now we integrate on both the side. So integral dh equal to integral beta to alpha minus I divided by 4 pi d into sin theta d theta. Minus I divided by 4 pi d is constant, it taken outside. Only we have sin theta. Integral sin theta is minus cos theta. You substitute the limit beta to alpha. So that minus I divided by 4 pi d into minus cos alpha. While substituting lower limit, one minus will be there. Already one minus is there. So it becomes plus cos beta. Minus cos alpha plus cos beta. Right? Here one negative symbol available. So you multiply inside. So what will happen? I divided by 4 pi d. This minus become plus cos alpha. This plus become minus cos alpha minus cos beta. So the magnetic field intensity due to finite conductor, the final expression is H equal to I divided by 4 pi d cos alpha minus cos beta. In this one, special condition is available. Suppose if the length is infinite, what we are assuming is finite conductor. We are assuming as finite conductor AB, the length is finite. Suppose if it is infinite, what will happen? The alpha is tends to 0 while going when the length is increases, the angle alpha is approaching to 0 and beta is approaching to 180 degree, right? So here cos alpha equal to cos 0, alpha is 0, so cos 0 means 1. Then cos beta is there, cos beta is equal to cos 180 degree, beta is 180 degree, cos 180 is minus 1. So cos alpha is 1, cos beta is minus 1. We can substitute here. H equal to I divided by 4 pi d, cos alpha 1 minus 1. Already one minus is there. So it become plus 1 plus 1, 2. So it become 2. Already here 4 is there. While cancelling it become 2. I divided by 2 pi d. Right? If the length is infinite, the magnetic field intensity after substituting this value, alpha approaching to 0, beta approaching to 180, what we got? I divided by 2 pi d. So in this video we discuss the magnetic field intensity due to finite conductor. We got the expression for that, and we have one special condition when if the length is infinite. What is the expression for magnetic field intensity? Thank you. Welcome viewers. In this video we'll see the magnetic field intensity due to circular current loop, followed by the two problems. Now we'll refer the diagram. One lengthy wire is available. That wire is two ends are joined together and the circular loop is formed. One lengthy wire will be available. That lengthy wire, two ends are connected together and form the circular loop. So the radius of the circular loop is a meters. Our aim is to find the magnetic field intensity at this point P, which is at a distance h meter from the center of the current loop. This current loop is assumed to be having several current elements, n number of current elements available. We consider one current element at this point, ideal vector. The distance between this current element and point P is r meter. The h is the magnetic field intensity, dh is magnetic field intensity due to ideal. There are n number of ideal available. We consider only one ideal, so that there is magnetic field intensity also small, dh. By integrating this dh, we will get total magnetic field intensity. Right? One lengthy wire available, the two ends of the wire is connected so that form the circular current loop. The radius a. Our aim is to find the magnetic field intensity at point P, which is at a height of h meter. There are n number of current elements available. In that we consider one current element at this point. The distance between this point and point P is r meter. The angle between this r and ideal vector is 90 degree. From the diagram it is clear. So this dh is the magnetic field intensity due to this small element, ideal. So this triangle is drawn separately. This angle alpha, height a and r. So from that we can find the sin alpha. Sin alpha is opposite side by hypotenuse, a divided by r. It can be used in the derivation. Right? Sin alpha equal to opposite side by hypotenuse, a divided by r. We'll see the description. So it is required to determine magnetic field intensity at point P, which is at a height of h meter from the center of the current loop. Right? The point P is located at a height of h meter from the center of the current loop. At that we are going to find the magnetic field intensity. How the circular current loop is formed? The circular current loop is formed by wire bent in the form of a circle. The wire is bent, two ends are connected together and the circle is formed. the loop is assumed to be formed by several current elements. There are n number of current elements available in the entire loop. In that we consider a current element ideal. The distance between this current element point P is r meter. Then this dh vector is the perpendicular to the plane containing vector ideal and r. In the diagram it is clearly shown. The angle between ideal and r is 90 degree. Now we'll go to the derivation. The normal component of magnetic field intensity is given by, because due to this wire we have only normal component. There is no horizontal, there is no vertical component, only normal component. So dh equal to dh cos 90 minus alpha. Normal component is, it is multiplied by cos of theta. Cos 90 minus alpha can be written as sin alpha. What is dh? From Biot-Savart's law, the standard form is available. Ideal vector cross r vector divided by 4 pi r cube into sin theta, sin alpha. So this is written from the Biot-Savart's law. What is a vector cross b vector? ab sin theta. So ideal r into sin theta. The angle between dl and r is 90 degree. So it is sin 90 degree. So ideal cross r vector is ideal r sin 90 into sin alpha divided by 4 pi r cube. Now here r is there, here r cube is available. So here this sin alpha is replaced by a by r. From the triangle we calculated sin alpha equal to a by r. So this r got cancelled. Sin 90 is 1. So finally what we have? I into a into dl, ia dl divided by 4 pi r cube. ia dl divided by 4 pi r cube. So this is due to only small current element. This dh is the magnetic field intensity due to small current element. So by integrating on both the side, we'll get the total magnetic field intensity. So integral dh equal to integral ia dl divided by 4 pi r cube. ia divided by 4 pi r cube is constant. Only we have integral dl. What is integral dl? Integral dl is L. L is nothing but 2 pi a. That is, one lengthy wire is available, length L. This wire is formed as a circle, as a current loop. So this radius is a. So the length of this wire is equal to circumference of this current loop. Both are equal. What is the circumference? 2 pi a. That is given. Length of this wire, because this wire only formed a circle. So the length is nothing but circumference. Both are equal. L equal to circumference. Circumference is 2 pi a. Right? So integral dl is L. L is nothing but 2 pi a. Here 4 pi is there. Here 2 pi is there. Got cancelled. 2 is there. So I into a square. I into a square divided by 2 r cube. I a square divided by 2 r cube. We got the value. We take it as equation number 1. H equal to I a square divided by 2 r cube. Now we'll see the other forms. So from the triangle we can write r equal to, using Pythagoras theorem, a square square root of a square plus h square. So from this triangle it is given r square equal to a square plus h square. So r equal to square root of a square plus h square. That is written. So r equal to, it can be written as a square plus h square whole power 1 by 2. Square root is written as 1 by 2. But in equation what we have? R cube. R cube is needed. ia square divided by 2 r cube. R cube means you multiply with 3. Already 1 by 2 is there. So 3 into 1 by 2 is 3 by 2. R cube equal to a square plus h square whole power 3 by 2. Right? So r equal to square root of a square plus h square. That can be written as a square plus h square whole power 1 by 2. Here 3 is needed, r cube is needed. So a square plus h square, 3 into 1 by 2, that is 3 by 2. Now we can substitute this value in the equation number 1. What is equation 1? H equal to ia square divided by 2r cube, right? So this r cube can be substituted from this a square plus h square whole power 3 by 2. So what will happen? H equal to ia square divided by 2 into a square plus h square whole power 3 by 2. So this is another form in terms of height. In the equation 1, what we have? A and R. A and R is available. A is the radius of the current loop, R is the distance. Here, and in terms of height is available. A and height. So this is another form. Suppose if the center of the current loop, if you consider the point P is located at the center, or what is the magnetic field intensity at the center of the current loop. So at the center of the current loop, what will happen? The height is 0. So the height is 0, so that h equal to ia square divided by 2 a square plus h square whole power 3 by 2. This height is become 0. This height become 0. So what will happen? Ia square, this a square into 3 by 2. So this 2 got cancelled. We will get a cube, right? So this what is available here is a square whole power 3 by 2. So this 2 got cancelled. What we have? A cube. So ia square divided by 2a cube. Here a square cancel, here 2 terms are cancelled. So what we have? I divided by 2a. This is at the center. At the center of the current loop, the magnetic field intensity is I divided by 2a. Suppose if n number of turns are available, what happen? ia square divided by r2 r cube into n. You have to multiply with number of turns, right? H equal to ia square divided by 2 r cube into n. That is due to n number of coils. Here we have only one circular current loop. If n number of current loop available, ia square divided by 2 r cube into n. So we have the 4 different expression available. First is ia square divided by 2 r cube. Then r is substituted in terms of height. That is the second expression. Then height is 0 at the center. That is third expression, this one. This will be fourth expression in terms of number of turns. Now we'll see the problem. We'll see the first problem. What is given? A wire carrying a current of 100 ampere is bent in the form of circle. So this is a circular current loop of diameter 10 centimeter. Right? See here, the current is 100 ampere, diameter equal to 10 centimeter means radius equal to 5 centimeter. That is 5 into 10 to the power minus 2 meter. So what is the question? Flux density at the center of the coil. First one, at the center. Flux density at a point form a axis of the coil and 12 centimeter away from it. That is at a height of 12 centimeter. Right? We discussed 4 different expressions available at the center, in terms of height, all are available. So first one is based on the center of the current loop. Height is 0. Second one based on the height. Height is 12 centimeter. Right? So the current and radius is given. Now we'll go to the first division. Magnetic field intensity at the center of the coil. What is the formula? I divided by 2a. At the center of the coil, height is 0. So only we have I divided by 2a. Already we got the expression. So I is 100 divided by 2 into a. A is nothing but radius. 5 into 10 to the power minus 2. So by simplifying, what we got? 1000 ampere turns per meter. This is the magnetic field intensity. But what we need is flux density. B is needed. So B equal to mu naught mu r into h. There is a relation between mu and h is available. B equal to mu naught mu r h. Mu naught is nothing but constant. 4 pi into 10 to the power minus 7. Mu r is 1. We assume that is a air medium. The height is, the magnetic field intensity is calculated. This 1000. Right? So by simplifying this, what we got? 1.25 into 10 to the power minus 3 Weber per meter square. Magnetic flux density is 1.25 into 10 to the power minus 3 Weber per meter square at the center of the coil. We have one more at the 12 centimeter. When it is the axis is placed at a height of 12 centimeter, that is height equal to 12 centimeter. That is 12 into 10 to the power minus 2 meter. For this, what is the formula? Ia square divided by 2 into a square plus h square whole power 3 by 2. So this expression also we got previously. This is in terms of height, right? So I is 100, a is 5. 5 into 10 to the power minus 2 square divided by 2 into 5 into 10 to the power minus 2 square plus height is nothing but 12 centimeter. 12 into 10 to the power minus 2 square whole power 3 by 2. You have to square this value, add both. For that we need to take 3 by 2, right? So by simplifying this value, what we got? 57.36 ampere turns per meter, okay, at the height of 12 centimeter. This is a magnetic field intensity, 57.36 ampere turns per meter. From that we can find magnetic flux density, B equal to mu naught mu r into H. So mu naught is 4 pi into 10 to the power minus 7, mu r is 1, and the magnetic field intensity what we calculated, 57.36. So by simplifying this value, what we got? 71.46 into 10 to the power minus 6 Weber per meter square. So this is due to the coil placed at 12 centimeter height, right? So this one due to it is placed at the center of the coil, right? We have two divisions, center of the coil and placed at a 12 centimeter, height of 12 centimeter. Now we'll see the next problem. So in the second problem, there are two narrow circular coils available, A and B, right? We'll see the diagram so that it is easier for you. So there are two circular current loops are available. The radius of the first circular current loop is 5 centimeter. Second current loop is 8 centimeter. The center to center distance is 15 centimeter. Right. The current flowing through the first coil is 2 ampere. Coil A is 2 ampere. But the current in the second coil is not given. We need to find. Right. So the radius of first one is 5 centimeter. Current is 2 ampere. Radius of the second coil is 8 centimeter. Current is not known. Center to center distance is 15 centimeter. So what is the other values are given? So the two circular coil A and B and placed at a distance 15 centimeter. Coil A has 10 turns available of radius 5 centimeter and the current is 2 ampere. But coil B has single turn of radius 8 centimeter. What is the condition? If the magnetic field at the center of coil A is to be 0, what current must be passed through coil B, right? So at the center of the coil A to be 0, in order we need to make it as this coil A is 0 such that what is the current is passing through coil B. So that is the question asked, right? So we'll see the what are the datas. The number of turns available for the coil A is 10, radius 5 centimeter, 5 into 10 to the power minus 2 meter, current is 2 ampere. For coil B, number of turns 1, radius is 8 into 10 to the power minus 2, the IB we need to find. So from the given condition, we can conclude that the magnetic field at the center of coil is 0. When it is 0, it is possible only when the magnetic field intensity due to the coil B, HB, due to the coil B at the center of the coil oppose the HA, which is equal and opposite, right? So magnetic field intensity of coil A, when it becomes 0, the magnetic field intensity due to the coil B oppose the coil A, and it should be equal and opposite. So the magnetic field intensity produced by coil B is opposing coil A and make it as 0. What is the meaning? Both are equal and opposite. HA equal to HB. That is the, from the given condition we got the expression HA equal to HB. So the magnetic field intensity produced by coil B oppose the coil A and make it as 0. right? So using this condition, we can find the current in the second coil. So first we will find the HA. HA equal to NAIA divided by 2A. That is at the center. The coil A we assumed at the center. Coil B we assumed at a height of 15 centimeter. Right? Coil A is a reference. So that it is at the center. NAIA divided by 2A. Normally I by 2A, but here number of turns available, so that NAIA divided by 2A. The number of turns is 10, current is 2 ampere, divided by 2 into the radius is 5 into 10 to the power minus 2. That is 200 ampere turns per meter. So the coil A we assume at the center. Coil B, it is at a height of 15 centimeter, because coil A and B, the distance, center to center distance between coil A and B is 15 centimeters. So that we are using this formula at a height, in terms of height, here at the center. So now we substitute the value. NB, the number of turns in the coil B is 1, right? Then IB value is not available. We need to find the IB value. Then B square, 8 into 10 to the power minus 2 the whole square, divided by 2 into 8 into 10 to the power minus 2, the radius of the second coil, plus the height is 12 into 10 to the power minus 2 whole square, whole to the power 3 by 2, right? So by simplifying this, what we got, 0.651 IB, right? So HB equal to 0.651 IB, right? This IB value is not known. Now we have the relation HA equal to HB. What is HA? We calculated 200. What is HB? 0.651 IB. So from that, IB equal to 2 divided by 0.651, that is 307.6 ampere. So the current flowing through the second coil B is 307.6 ampere. So due to this current flow, the magnetic field produced in the coil B will oppose coil A and make it as 0. So in this video, we discuss about the magnetic field intensity due to circular current loop, followed by 2 different problems. Thank you. Welcome viewers. In this video, we'll see the magnetic field intensity due to the solenoid. What is solenoid? Solenoid is an electromagnet. It is formed by winding few turns over an iron rod. So this is the iron rod is there. Over that, the coils are winded. If the supply is given, it becomes the electromagnet. So the solenoid is nothing but iron rod is available. Over that, the coils are winded. When the supply is given, it becomes electromagnet. So our aim is to find the magnetic field intensity at the center of the solenoid. It is required to determine magnetic field intensity at the center of this solenoid. Now we'll go to the detailed diagram. So the length of the solenoid is AB. We consider length of the solenoid is AB. This is at the center. Point P is located at the center. For calculation purpose, we consider one small segment at a distance x meter. The thickness is dx. The number of turns available is n into dx. So at point P, at a distance x meter, we consider one small segment dx. The number of turns is n into dx. By integrating, we will get the total magnetic field. The distance between this point P and this end is r meter. This distance is a meter. This angle is theta. So this triangle is drawn separately here. Theta, x, r and a. The angle between point P and point B is alpha. Similarly, point P and point A is pi minus alpha. So this will be alpha. So automatically the remaining will be pi minus alpha. Right. So we have the solenoid with length AB. Our aim is to find the magnetic field intensity at the center of the solenoid. So point P is located at the center. The small segment is available at a distance x. The thickness is dx. Number of turns is n into dx. This angle is theta. This distance is r. This distance is a. This triangle is drawn separately. The angle corresponding to point A is pi minus alpha. The angle corresponding to point B is alpha. Right, now we'll see the description. A solenoid is assumed to be formed by several circular current loop. Right, so the circular current loop derivation available in separate video. You can refer that. In this solenoid, what we are assuming, there are n number of current loops are available. Each and every coil is a current loop. Consider a segment of the solenoid at a distance x meter from the point P. We consider one segment dx at a distance x meter. The number of turns in this section is n into dx. Right. What is the magnetic field intensity due to this small segment? The dH is the magnetic field intensity due to n into dx turns at point P, which is given by dH equal to Ia square divided by 2r cube into n into dx. Right. So this is due to only small segment with n number of turns, n into dx. How we got this expression? That is from circular current loop. Circular current loop derivation already available in another video. Right. From that we are referring this. So this is also circular current loop. Here n number of circular current loops are available. So that is multiplied by number of turns, n into dx. This is circular current loop expression, Ia square divided by 2r cube. In that, n number of turns are multiplied. We take this equation number 1. Now we'll find the expression for r and dx from the triangle. One separate triangle is available. From that, we will find the expression for dx and r. So refer this triangle, which is already available. So I drawn again here. The angle is theta, x, r and a. Now we'll find the expression for tan theta. What is tan theta? Is tan theta equal to opposite side by adjacent side, a divided by x. Now cross multiply this. So x equal to a by tan theta. 1 divided by tan theta is cot theta. What we need is differentiation. We need a differentiation. We need a dx. So differentiate on both the side. Dx equal to differentiation of a cot theta. So the a is constant. The differentiation of cot theta is minus cosecant square theta into d theta. So finally what we have? Minus a cosecant square theta d theta. The expression for dx is minus a cosecant square theta into d theta. Now we got the expression for dx. Similarly, find sin theta, expression for sin theta. Sin theta equal to opposite side by hypotenuse, a divided by r. Again here cross multiply this. Bring the r here, sin theta here. So r equal to a by sin theta. So 1 divided by sin theta is cosecant theta. So r equal to a cosecant theta. Now we got the expression for dx and r that can be substituted in equation number 1. Right? Substitute the value of dx and r in equation 1. What is equation 1? Ia square divided by 2r cube into n into dx. This is the equation 1. So Ia square into n, dx is nothing but minus a cosecant square theta into d theta. So that is available here. Dx equal to minus a cosecant square theta into d theta divided by 2 into r cube. What is r value? R is nothing but a cosecant theta. Right? So that a cube into cosecant cube theta. The dx value substituted and r value substituted. See that here cosecant square is available, here cosecant cube is available. So these two got cancelled. Cosecant square dot cancel. 1 cosecant theta will be available. Here a cube is available, here a square and a is available. So totally all are cancelled. So finally what we have? I into n into d theta divided by 2 into cosecant theta. 1 cosecant theta is available here. Right? So minus also there, this minus also there, minus in d theta divided by 2 cosecant theta. So 1 divided by cosecant theta is written as sin theta d theta, right? So dh equal to minus I into n divided by 2 sin theta d theta. So this is due to only small segment. So by integrating, we will get the total magnetic field intensity. Intensity due to entire solenoid can be obtained by integration. Now we'll see the integration. What is the limit for the integration? So when the length of the solenoid is AB, at the end AB the angle is pi minus alpha. So this is one limit. At the end B the angle is alpha. This is another limit. How it is? By moving the strip from A to B, the magnetic field intensity due to the entire solenoid can be obtained. Therefore, the limit is from pi minus alpha to alpha. That is A to B. A is pi minus alpha, B is alpha. So the limit is from pi minus alpha to alpha. Right? Now we'll go for the integration. So integral dh equal to integral pi minus alpha to alpha minus I into n divided by 2 sin theta into d theta. Just now we got the expression. So in that minus I by n divided by 2 is constant. Only we have sin theta d theta with a limit pi minus alpha to alpha. So minus I n divided by 2, integral sin theta is minus cos theta with a limit pi minus alpha to alpha. Now we'll substitute the limit. Minus in divided by 2, this substitute the upper limit minus cos alpha. While substituting the lower limit, we already one negative is there, it become positive. So this will be theta, not a alpha, theta. Pi cos pi minus alpha. So upper limit is substituted and lower limit also substituted. Due to negative, it become positive. So already one negative available outside, so multiply inside, so it become positive, it become negative. In divided by 2 cos alpha minus cos pi minus alpha. So in divided by 2 cos alpha, cos pi minus alpha is nothing but minus cos alpha. Cos pi minus alpha can be written as minus cos alpha. Already here one minus is there, here also minus is there, so it become plus. So in divided by 2 cos alpha plus cos alpha. So that is nothing but in divided by 2, 2 cos alpha. So 2 got cancelled. I into n into cos alpha. Right? So the magnetic field intensity due to the center of the solenoid is I into n cos alpha. Now we'll see the one more special case if it is long solenoid. Suppose the solenoid is infinite long. If it is infinite long, what will happen? The alpha value is 0. So that cos alpha, cos 0 means 1. So the magnetic field intensity become I into n. I into n into cos alpha. The cos alpha now become 1. Right? So this is the magnetic field intensity due to infinite long solenoid. One special case. From this equation, what we understand, magnetic field intensity due to a long solenoid is uniform. It does not vary with the distance, right? So the magnetic field is uniform. Here the distance is not available, only current and number of turns. So it means that the magnetic field is always uniform. It does not vary with the distance. So in this video, we discuss the magnetic field intensity due to the center of the solenoid, derivation, and one special case, infinite long solenoid. What is the expression for infinite long solenoid? Thank you. Welcome viewers. In this video, we'll see the magnetic boundary condition. There are two boundary conditions available, first boundary condition and second boundary condition. First we'll see the first boundary condition. The boundary is nothing but two different magnetic materials are combined together. The line separating the two magnetic materials called a boundary. So now consider a magnetic boundary formed by two different magnetic material with permeability mu r1 and mu r2. So we have the two magnetic materials are combined together that form the boundary with permeability mu r1 and mu r2. When the flux lines are coming out of this boundary, its magnitude and direction changes. When the flux line flow from one magnetic material to another magnetic material, what will happen? There will be a change in magnitude and direction. So that we are going to study in this boundary condition, whether there is any change in the flux while entering into one magnetic material to another magnetic material, whether there are equal or there may be some difference is there, any deviation is there in the magnitude and angle, we are going to study in the boundary conditions. Now consider this consider this diagram. So this is the first magnetic material. 1 refers the first magnetic material with permeability mu r1. This 2 refers the second magnetic material mu r2 with permeability mu r2. Both are combined together. It is separated by this line. So this line is nothing but a boundary between first magnetic material and second magnetic material. Right? So the line is nothing but a boundary. We consider one box is placed at the boundary such that it half of available in the first magnetic material, half available in the second magnetic material. Right? So the surface area of this box is delta S, height of this box is delta H. What we are going to analyze? The normal component of flux density vector. This is normal component of flux density vector entering the box Bn2. Bn1 is the normal component of flux density vector leaving the box. So this flux density vector enters in the second magnetic material and leaves in the first magnetic material. So it is enter in second magnetic material, leave in the first magnetic material. So whether both are equal, we are going to analyze. Because of two different magnetic material, any deviation in the normal component of flux density vector, any deviation is there, that we are going to analyze. So this vector diagram is given. This B2, this is a normal component of flux density. This is a flux density B2 and B1. Theta 2 is the angle of incidence. Incident means entering. Theta 1 is the angle of emergence. Emergence means leaving. Right? So our aim is we need to analyze whether this Bn1 and Bn2 both are equal or there is any deviation is there, that we are going to analyze. Now we'll see the description. B1 and B2 be the flux density in media 1 and 2 respectively. Media means magnetic material. Right? B1 and B2. Theta 2 is angle of incidence. Theta 1 is the angle of emergence. Then Bn1 and Bn2 are the normal component of flux density vector in media 1 and 2 respectively. Normal component. Now we construct a box such that it encloses both the media. That box covers both the magnetic material 1 and magnetic material 2. Now we will analyze that according to Biot-Savart's law. We will analyze based on Biot-Savart's law. Integral B dot ds equal to 0. Flux density in a closed path is equal to 0. Then what is the flux entering the box? Bn2 into delta S. Already we refer the diagram. The flux density entering the box is Bn2 into delta X. Right? So the flux. So B is nothing but pi by S. So that pi equal to B dot S. Right? So by cross multiplying this we will get. So this Bn2 is the flux density vector. Flux is nothing but flux density vector multiplied by surface area B dot ds. So that here Bn2 dot ds, because Bn2 is the entering the box. Similarly, flux leaving the box is Bn1 into delta S. Right. So according to Biot-Savart's law, what is that? The net flow of flux is 0. That is, difference between these two is 0. Bn2 delta S minus Bn1 delta S equal to 0. This delta S is common. So Bn2 minus Bn1 of delta S equal to 0. So this delta S become 0. So Bn2 minus Bn1 equal to 0, that is Bn2 equal to Bn1. What is that? Flux density entering and leaving both are equal. There is no change in the magnitude and direction. Both are equal. Why? There is no charged sheet available. If any charge is available at the boundary, that will make the deviation in magnitude and direction. But in our diagram, there is no charged sheet available, so that directly we are getting these two are equal, right? So the statement is given. Normal component of flux density vectors are equal. Otherwise, normal component of flux density vector is continuous at the boundary. Continuous means there is no deviation, right? Now we'll go to the second boundary condition. So the second boundary condition, before going to that, we'll see the sheet current density. What is sheet current density? K equal to current per unit length. I divided by del L is nothing but the current density. So from that, I equal to K into delta L. You cross multiply this, I equal to K into delta L, right? It can be used in the derivation. Now this is the second magnetic material. These two refers the second magnetic material. This one refers the first magnetic material. Both are combined together. This line is the boundary between second magnetic material and first magnetic material. In the first boundary condition, we deals about normal component of flux density vector. In second boundary condition, we are dealing with tangential component of magnetic field intensity. Tangential component of magnetic field intensity we are going to deal in the second boundary condition. Here what we have, one closed loop is available, A, B, C, D, A. One closed loop is available. So it covers both magnetic material 1 and magnetic material 2. It covers both the magnetic material. The length is delta L. The height is delta H. The magnetic field intensity in the path AB is HT1. In CD is HT2. But see the direction, both are opposite. What about the magnetic field in the BC and DA? That is 0, because in a perpendicular path that is 0. And also the height is approaching to 0 means these two are 0. Only we have AB and CD. And our important thing, we have one infinite current sheet of charge density K is placed at the boundary. In first boundary condition, we are not placed any charged sheet. Now we are placing one infinite current sheet at the boundary, right? So the description is available. HT1 and HT2 are the tangential component of magnetic field intensity in media 1 and 2. That is magnetic material 1 and 2. Construct a rectangular path ABCDA such that it encloses both the media. Now we apply the Ampere's law to the path ABCDA. We are going to apply the Ampere's law. What is Ampere's law? Integral H dot dl equal to I in a closed path ABCDA. Right? In a closed path ABCDA, integral H dot dl equal to I. Now we'll go for the further simplification. Now the ABCDA, closed path ABCDA is now split into 4 parts: AB, BC, CD and DA. 4 different parts, that is equal to I. Now we assume that the delta H is approaching to 0. That means this BC and DA become 0. There is no term BC and DA because height is nearly equal to 0. Only we have AB and CD. What is the magnetic field intensity in AB? HT1 into delta L. We already referred in the diagram. What is the magnetic field intensity in CD? Minus HT2 into delta L, because the directions are different. Vector direction is different, so that we have got negative. That is equal to I. So HT1 delta L minus HT2 delta L, that is equal to This I is nothing but K into delta L. Already we got that current density. So this delta L available everywhere, we can cancel. So HT1 minus HT2 equal to K. What is that? The magnetic field intensity, tangential component of magnetic field intensity are not equal. It is depends upon the current density, right? The current density of the charged sheet. In the first boundary condition, we got Bn1 equal to Bn2 directly, but here not equal. Why? That's due to the current sheet of charge density K, right? That is depends upon the K value. Suppose if the current sheet is not available, if sheet is not present, then K equal to 0. If K equal to 0 means HT1 minus HT2 equal to 0, so that HT1 equal to HT2. Now both are equal. When if it is no charged sheet is available, then only both are equal. That is given. Tangential component of magnetic field intensity vectors are equal, right? So it is very clear, the magnetic field intensity or flux density is equal only if there is no charges available. If any charge is available in the boundary, that will affect the direction and magnitude of the either flux density or magnetic field intensity. So in this video we discuss about the boundary condition, first boundary condition and second boundary condition. Thank you. Welcome viewers. In this video we'll see the Ampere's law definition followed by applications of Ampere's law. First we'll say the statement of Ampere's law. The statement is the line integral of tangential component of magnetic field intensity H around a closed path is exactly equal to the current enclosed by that path. Suppose if conductor is available, current is flowing through the conductor, the magnetic field is produced in and around the conductor. That magnetic field is equal to amount of current enclosed in the conductor. That is the statement given by the Ampere's law. Integral H dot dl equal to I. So when a current is flowing through a conductor, the magnetic field is produced. So the magnetic field is equal to amount of current enclosed in that path. The closed path is required while applying the Ampere's law. So in the closed path, the entire magnetic field intensity is equal to current flowing through that closed path, right? So it's a statement given by Ampere law is integral H dot dl equal to I. Now we'll see the applications of Ampere's law. There are 3 applications available. We'll see one by one. The first application is magnetic field intensity due to long wire. The magnetic field intensity due to finite wire is available in separate video. This is long wire, right? Finite wire means the length is defined, but here the length is not defined. It's a long wire. Now consider the circular loop with radius d meter, right? So refer this diagram. We are considering one circular loop with diameter d. So this is nothing but the conductor. The conductor, current I is flowing through the conductor. So due to this current flow, the magnetic field is produced in and around the conductor. In order to apply the Ampere's law, we construct one circular current loop with radius d meter. According to Ampere's law, what is that? Integral H dot dl equal to I. So the H is constant, so integral dl equal to I. What is integral dl? Integral dl is nothing but perimeter of this circular current loop. For example, this circumference of the circular current loop is nothing but a integral dl. That is integral dl is L. L is nothing but length. Length is nothing but circumference. So that is equal to 2 pi d, right? So integral H dot dl equal to I. So H into integral dl equal to I. Integral dl is L. L is nothing but perimeter, that is nothing but 2 pi d, right? So we can replace this integral dl with 2 pi d. So H dot 2 pi d equal to I. So H equal to I divided by 2 pi d, right? So this is the magnetic field intensity due to a long wire. So this magnetic field intensity depends upon two parameters. What is the current flowing through the conductor and the circular current loop, the radius of the circular current loop D, right? It is inversely proportional. Current is directly proportional. D is inversely proportional, right? So the final expression is H equal to I divided by 2 pi D. Now we'll see the second application. The second application is magnetic field intensity due to the solenoid. Due to long solenoid. This is also a long solenoid. Right? The magnetic field intensity due to normal solenoid available in a separate video. This is application of Ampere's law under that magnetic field intensity due to a long solenoid. You know that the solenoid is an electromagnet. It's an electromagnet. It is formed by winding few turns over a iron rod. Right? One iron rod is there over which if the coils are winded, when the current is flowing through the coil, it becomes electromagnet. So that is nothing but solenoid. Solenoid is a over a iron rod, the windings are available. When the supply is given, it becomes electromagnet. Now consider the solenoid with length L as shown in the diagram. Right? We are going to consider the solenoid with the length L meters. So this is the solenoid. This is the iron rod over which the coils are winded. When the supply given, it becomes electromagnet. The length of the solenoid is L meters. In order to apply Ampere's law, what we need is closed path is needed. When closed path is needed, then only we can apply the Ampere's law. So this closed path is A, B, C, D, A. So this path AB is available inside the solenoid, the CD available outside the solenoid. So that we can analyze what is the magnetic field intensity inside as well as outside of the solenoid. Right? So this is the iron rod over which the coils are available. When the supply given, it becomes electromagnet. The length of the solenoid is L meter. In order to apply the Ampere's law, we construct one closed loop AB, CD, A is such that AB available inside the solenoid, CD available outside the solenoid. Now we'll see what is the magnetic field intensity inside and outside the solenoid. Let us consider H1 is the magnetic field intensity available inside the solenoid. H1. H2 is the magnetic field intensity outside the solenoid. Right? We assume that we consider H1 is the magnetic field intensity inside the solenoid. H2 is the magnetic field intensity outside the solenoid. Now we can apply the Ampere's law. Apply Ampere's law to the closed path A, B, C, D, A. We'll see what is the Ampere's law. Integral H dot dl equal to I. We need to see what is the work done along this AB, BC, CD and DA. For all four paths, what is the work done? We need to analyze. The work done along AB is H1 into L, because the magnetic field intensity inside the solenoid is H1. So H1 into L, integral H dot dl. So H1 into L. The work done along CD outside is H2L. We assume that magnetic field intensity outside the solenoid is H2, right? So inside the solenoid H1, outside the solenoid H2. The work done along the path AB that is available inside is H1L. Work done along CD that is available outside is H2L. Then what is the work done along BC and DA? So work done along BC and DA is 0. Why? The magnetic field intensity and DL are perpendicular. Both are perpendicular to each other. So the magnetic field intensity in the path BC as well as DA is 0. Only the magnetic field intensity, the work done available along AB and CD. BC and DA is 0 because of perpendicular. So due to that, what we have, H1L plus H2L equal to N into I. The work done inside the solenoid, work done outside the solenoid, that is equal to current. Here N number of turns available, so that it is multiplied by Ni. So H1L plus H2L equal to Ni. Right. Now we'll see what is H1, what is H2. So the entire magnetic flux is flowing through the coil of the solenoid. Right, when the current is passed through the solenoid, the entire current is flowing through the solenoid. That is, the flux outside the solenoid is zero. We assume that entire flux is available only inside the solenoid. Outside the solenoid, the flux is zero. That is, H2 is zero. So that the flux flowing through the least reluctance path. So it will follow the least reluctant path that is available in the iron rod. Outside, the iron rod is not there. So outside, the magnetic field intensity is zero. Why? It follows the least reluctance path. So only H1 is available. H1L equal to Ni. This term become 0. So H1L equal to Ni means from that H1 equal to Ni divided by L. So here also the magnetic field intensity depends upon what is the current flowing through the coil, what is the number of turns in the coil, and what is the length of the solenoid. So these three parameters will decide the magnetic field intensity of long solenoid. H1 equal to Ni divided by L. Now we'll see the third application. The third application is magnetic field intensity due to infinite current sheet. One infinite current sheet is available. In that we are going to find what is the electric field intensity. So before that we see what is current density. Right? An infinite current sheet can be assumed to be formed by several sheets in parallel. Infinite current sheet means there are n number of sheets available that are placed in a parallel, like a notebook. Each and every paper is the parallel is the infinite current sheet. Like that, n number of papers are arranged in a parallel. So linear current density or sheet current density is nothing but current per unit length. Always the density means either area, volume, or length will be referred. Here we are referring the length of the current sheet. Right? So linear current density is nothing but current per unit length, that is K equal to I divided by delta L, ampere per meter. So I equal to K into delta L. So you can cross multiply this so that I equal to K into delta L. So that can be used in the derivation. Right? So we have infinite current sheet is available. We assume that there are n number of sheets available in parallel. So the current density is nothing but current per unit length, ampere per meter. From that we can find current equal to the current density into delta L. I equal to K into delta L. Now we'll see the diagram. So this is nothing but a infinite current sheet. The magnetic field available is H. The infinite current sheet is available. In order to apply Ampere's law, what we need? One closed path. A, B, C, D, A. We construct one closed path A, B, C, D, A in the infinite current sheet. The path is available inside, the path is available outside. The closed path, part is available inside, part available outside. The length of the closed loop is delta L. Right. So an infinite current sheet is shown in diagram. This is the infinite current sheet. Let us consider the rectangular path A, B, C, D, A. A, B, C, D, A. Now we are going to apply the Ampere's law to the closed path A, B, C, D, A. So while applying Ampere's law, definitely we need one closed path. Right. So according to Ampere's law, integral H dot dl equal to I for a closed path A, B, C, D, A. Right. For a closed path A, B, C, D, A. Now that is split into four parts: A, B, B, C, C, D, and D, A. So integral H dot dl for a path A, B. Integral H dot dl for a path B, C. Integral H dot dl for a path C, D. Integral H dot dl for a path D, A, that is equal to I. So what is the work done along these four different paths? The work done along BC and DA is 0 because the magnetic field intensity is 0 in normal direction. In the previous derivation solenoid also we did like that. For BC and DA, it is normal direction, so the magnetic field intensity is 0 for BC as well as DA. What about AB and CD? The magnetic field available in AB and CD. See this, for AB, the magnetic field intensity will be H. Similarly, for CD, the magnetic field intensity will be H. Only for BC and DA, it becomes 0 because of normal. Right? So now we can apply this. For a path AB, H into DL. There is no H1, H2. We assumed only H into DL. For BC, it is 0 due to normal direction. And CD, again H dot DL outside. Then this DA also 0. That is equal to I. I can be replaced as K into DL. That is current density. From the current density we already discussed. Right? So H DL plus H into DL. So it becomes 2H into DL. That is equal to K into DL. The DL got cancelled. 2H equal to K. From that, H equal to K divided by 2. So magnetic field intensity due to finite current sheet, the final expression is H equal to K by 2. So this is depends only on the current density of the current sheet. Right? H equal to K divided by 2. So in this video, we discuss the Ampere's law statement followed by applications of Ampere's law. 3 different applications we discuss. Infinite long wire, long solenoid and infinite current sheet. Thank you. Welcome viewers. In this video we'll see the magnetic potential. There are 2 types available, scalar magnetic potential and vector magnetic potential. First we'll see the scalar magnetic potential. It is denoted by U. Scalar magnetic potential by the symbol is U. So we know that the E equal to minus del V. The relation between E and V, electric field intensity and potential is E equal to minus del V. The del is nothing but the partial differentiation x, y, z. If it is rectangular coordinate x, y, z. Similarly, for magnetic potential is given by H equal to minus del U. Here E is replaced by H, V is replaced by U. Right? So if we consider this is for electric field. If it, in case of magnetic field, the same thing is given as H equal to minus del U. Now take curl on both sides. While taking curl, what will happen? Curl H equal to minus curl of del U. Right? The curl H equal to minus curl of del U. That is nothing but curl H equal to minus curl. This del U is nothing but gradient U. The del U can be replaced by gradient U. But we know that curl H equal to 0. Curl of H equal to 0. But according to Ampere's law, curl of H equal to J, current density. Right? So the normal derivation, normal expression, curl of H equal to 0, but based on the Ampere's law, the curl of H equal to J. Right? These two are not matching together. So from the above relation, the Maxwell's concluded that the concept of scalar magnetic potential is applicable only for magnetic field produced by permanent magnets. Right? So the scalar magnetic potential is applicable only permanent magnets, not a electromagnet. Right? So the Maxwell's concluded that these relations are applicable only for permanent magnet, not a electromagnet. So this concept cannot be applied to the field produced by steady current. That is not possible to apply for the permanent magnet can be applied, not a electromagnet. Cannot apply for electromagnet produced by steady current. So from that what we can conclude, we know that integral E dot EL equal to V. Similarly, integral H dot equal to U, the scalar magnetic potential, right? But according to Ampere's law, integral H dot dl equal to I, right? So based on this, integral E dot dl equal to V means H dot dl equal to U. But Ampere's law gives H dot dl equal to I. So by comparing these two, these sides are equal, integral H dot dl. So these two expression in these two sides also equal, so that U equal to I. That is, scalar magnetic potential is equal to current, right? So we can represent scalar magnetic potential is nothing but a current. So that is given here. The unit of scalar magnetic potential is amperes, right? So we conclude that U equal to I, the unit is amperes. Now we'll see the vector magnetic potential. So vector magnetic potential is denoted by the term A. What is vector magnetic potential? The dA. The A is the magnetic potential. dA means magnetic potential due to small length L. L is the length, small length dl. So due to that, the magnetic potential, vector magnetic potential become dA. So that is, so the dA is the magnetic field potential due to the current element IDL. Current element is nothing but I into dl. That already you know that. So due to this current element, the magnetic field intensity is dA. So this dA is proportional to IDL and inversely proportional to distance r. The distance between the IDL and point P is r, right? So this dA is directly proportional to IDL vector and inversely proportional to r, distance between the point and current element. So while equating, we introduce one constant, that is mu by 4 pi IDL divided by r. So the dA can be expressed as mu by 4 pi IDL by r. So this dA is the magnetic potential, vector magnetic potential only due to small element IDL. So by integrating on both the side, we will get the total vector magnetic field. Now we can refer this diagram. So this is the current element I. Here this is the conductor. The current is flowing through this conductor. Here n number of current elements available. We consider one current element IDL. We need to find what is the magnetic vector magnetic potential at this point P, which is at a distance r meter, right? So due to the small current element dl, we represented as magnetic potential as vector magnetic potential as dA, right? So this is the conductor available. The current is flowing through the conductor. Magnetic field is produced. This conductor is assumed to be having so many current elements. We consider only one current element. The magnetic potential due to this current element at point P is dA. This point P is located at a distance r meter. So the magnetic field intensity magnetic potential due to entire conductor can be obtained by integration. So integral, this expression is available. By integrating this, we will get the total vector magnetic potential. So integral dA equal to integral mu divided by 4 pi IDL vector by r vector. So integral dA is nothing but A. That is equal to mu by 4 pi, integral mu by 4 pi IDL vector divided by r. Now for the simplification, multiply and divide with the term area A, right? We are going to multiply and divide by the term A. So what will happen? So A vector equal to integral mu divided by 4 pi IDL vector divided by r into A divided by A. So the originality will not affect. Area, the term area, A by A. So it is rewritten as A vector equal to mu by 4 pi is constant, that is taken outside. Integral I by A, we are combining these two parameters, I by A into dl divided by r, right? So this I divided by A is written here, dl A written here, and A is r is written here. What is I by A? Current by area, that is nothing but current density. What is A into del? Area into length, that is nothing but volume. Right? I by A is nothing but the current density. Current per unit area is nothing but current density. Area into length is nothing but volume. So that A vector, the vector magnetic potential equal to mu divided by 4 pi integral J current density, J dot dV volume divided by R. So this is the final expression for vector magnetic potential. So in this video we discuss about the magnetic potential, the two types, scalar magnetic potential and vector magnetic potential. Thank you. Welcome viewers. In this video we'll see the force between two current carrying conductors, force between current loop and torque on the closed circuit. These three derivation we will see today. So the first one is the force between two current carrying conductors. There are two current carrying conductors available. In between, what is the force is available. Now consider this diagram. So this is the conductor A, this is conductor B. There are two conductors available, conductor A and conductor B. The current flowing through the conductor A is I1, current flowing through the conductor B is I2, I1 and I2. In order to apply Ampere's law, we construct the current loop covering both conductor A and conductor B. Only one current loop is available here. Two conductors are there. Commonly we constructed one current loop. The diameter is d meters. The length of the conductor is L meter. So we have two conductors A and B. The current flowing is I1 and I2. The circular current loop is available covering conductor A and B. The diameter is d and the length is L meter. Right? So that is given here. Consider two current carrying conductors A and B with current I1 and I2 as shown in the diagram. The distance between the conductor is d meters. The loop is formed to cover both the conductors. Now we'll see what is the magnetic field intensity due to conductor A. First we'll consider conductor A. What is the magnetic field intensity due to infinite current carrying conductor? That is H equal to I1 divided by 2 pi d based on the Ampere's law. Integral H dot dl equal to I. From that H equal to I1, because conductor A it is I1. Conductor A, the I1 current is flowing. I1 divided by 2 pi d. Then what is magnetic field intensity? Magnetic flux density? B equal to mu H. The relation is available. B equal to mu H. So the magnetic flux density B equal to mu into the H. H is nothing but I1 divided by 2 pi d. So B equal to mu I divided by 2 pi d. So this is referring the conductor A. Magnetic flux density of conductor A is nothing but mu I1 divided by 2 pi d. Then we'll see what is the force between the conductors. So due to conductor A, the force is developed on conductor B. The force experienced by the conductor B due to the magnetic field produced by conductor A. Right? We already found the expression for B for the conductor A. Now the force is experienced by conductor B due to magnetic field intensity of conductor A. What is the general formula? F equal to BIL. That is the general formula. Magnetic flux density, current and length. Here BI2, because of conductor B it is given as I2. B into I2 into L. This B already we calculated. The magnetic flux density due to conductor A, that is mu I1 divided by 2 pi d into I2 into L. Right? So this B is replaced as mu I1 divided by 2 pi d. So what is final expression? Force between the current carrying conductors mu I1 I2 L divided by 2 pi d. So this force between the conductor depends upon current in the conductor A, current in the conductor B, length of the conductor and diameter of the closed loop, circular loop. These parameters will decide the force between the conductors, right? So this is the force between two different conductors having only one circular current loop. Now we'll go to the force between the current loop, two different current loops, two different conductors with two different current loop. The second one we'll see force between the current loops, right? You see here, see, refer this diagram. So this is one current loop, this is another current loop. Here one conductor is there, here another conductor is available. So in the previous derivation, two conductors with only one current loop is formed, but in this derivation, two current loop is formed for two different conductors. So this is conductor A, the current flowing is IA. For that we consider one circular loop, the radius is A meter. This is conductor B, the current flowing is IB. Here we construct another circular current loop with radius B. The center to center distance between this current loop is x meter, right? So the conductor A, current is IA, the circular current loop radius is A, small a. Conductor B, the current carrying by the conductor B is IB, the radius of circular loop is small b. The center to center distance between the current loop is x meter, right? So that is given here. Let us consider two parallel coaxially placed circular loop of radius A and B, right? The centers are separated by x meters. The current in the coil is IA and IB, right? So due to two different current loop, we will find what is the mutual inductance between the current loop. Mutual inductance M equal to mu divided by 4 pi double integral dl1 dl2 divided by r. So this is the formula for mutual inductance between the current loop, right? What is here? The double integral is available, that is integral dl1 and integral dl2. What is integral dl1? Integral dl1 is nothing but L1. L1 is the length. Length is nothing but circumference. The circumference 2 pi a, circumference of this circular current loop. That is circumference of this circular current loop. Similarly, circumference of this current loop, right? So the dl1 equal to 2 pi a. Similarly, dl2 is L2. L2 is nothing but circumference of the second loop, 2 pi b. Here r we consider as x. Distance between the center to center distance between the circular current loop is x. Now we can replace integral dl with 2 pi a, integral dl2 with 2 pi b, r with x in this expression. So m equal to mu by 4 pi, integral dl1 is 2 pi a, integral dl2 is 2 pi b, and r is x, right? This dl1, dl2 and r is replaced here, right? So after simplification, what we got? This 2 pi available, here 4 pi available, so 2. These 2 and these 2 got cancelled. So finally what we have? This mu pi a b by x, that is pi mu a b divided by x, right? The mutual inductance between these two conductors. Now from that we can find the force between the current loop. What is the force between the current loop? The force between two coil with the current IA and IB is given as F equal to IA IB dm by dx. So this is the current in the first coil, current in the second coil. D by dx means differentiation of mutual inductance with respect to x. Distance, center to center distance between the coil x, right? We need to differentiate the expression mutual inductance with respect to x. Now we'll substitute the value of m here. IA IB d by dx of the mutual inductance, what we calculated as pi mu AB divided by x, right? So this m is replaced by this expression. So this IA IB, pi mu A is constant. Only what we have? D by dx of 1 by x. Only this 1 by x. We need to differentiate only 1 by x. Pi mu AB is constant. What is differentiation of 1 by x? Minus 1 by x square. So IA, IB, mu pi AB into differentiation of 1 by x is minus 1 by x square. So finally what we got? Force between the current loop, right, is minus IA, IB, mu pi AB divided by x square. So the force is depends upon current in the first conductor, current in the second conductor, right, radius of the first loop, radius of the second loop, and square of the distance between the center to center distance between the current loop, right. So this is the final expression. Now we'll see the torque on the closed circuit. Now we'll see torque on this closed circuit. Refer this diagram. So this we have one conductor AB, BC, CD and DA. Right? We consider this is one conductor AB. This is another conductor CD. This is another conductor DA and AB. One closed loop. The conductors are placed in a closed loop. The length is L meter. The width is W. This is x-axis and y-axis. This point P and Q is exactly placed at the midpoint. The point P is the midpoint. Now we need to see what is the force between this conductor and what is the torque between this conductor. Finally, what is the torque developed? Right? It is a rotating coil. If it is rotating coil, the torque will be produced. Right? So we have four conductors AB, BC, CD and DA. The length is L, width is W. The point P is located exactly at the half of the length of the conductor. We know that the torque, the force on this BC and DA is 0 due to normal. Only the force available in AB and CD. Right? We will see this one by one. The conductor AB is placed in the field with uniform distribution. That is, conductor AB is placed in the electric field. Similarly, CD also placed. First we consider AB, then we can go for CD. That's why only given AB. Then what is the another description? The P is the midpoint of AB, where AB has the length L. Right? The point P is located at the midpoint. The current flow from A to B. In this diagram, the current is flowing from A to B. In case of C, it is going from C to D. This one current is going upward, this current is going downward. The field is directed from parallel to x-axis. Then the force on the each element of DL of AB is. The L is the total length, DL means small length in the conductor AB. What is the force? IDL into B. The general formula is available, BIL. Current length into B. So that I into BL, we can write like this. So the total force on conductor. Now only consider AB. What is the total force on conductor? AB is I into B into DL. In case of CD, it is minus I into B into DL. Right? So which means that the magnitude of force is IBL. Both are same, only the direction is negative. The direction along y-axis is negative, right? So both are, the magnitudes are both are same. IBL, here also IBL. This negative sign indicates the force on the y-axis is negative. If we consider the loop ABCDA with the dimension L into W, the total torque on this loop is given as a torque equal to 2 into torque on each side. We consider AB and CD, right? So the total torque is nothing but 2 times of torque on each side. What is the formula for torque? Force into distance between the axis of rotation. That is the general formula. Torque equal to F into distance, right? So the 2 times, because we consider on both the side. So 2 into the force we already calculated, IBL. For both AB and CD is IBL. Only the negative sign is there. That indicates it is going in negative direction. The distance from the axis of rotation is W by 2, because W is the width, the point P is located exactly at the half, so that's W by 2. So these two got cancelled. So finally what we got, IBLW, right? That can be written as I into WL into B. What is W into L? Width into length, that is nothing but area, right? So the WL can be replaced. WL is nothing but A, right? So that torque equal to I into A into B. Current, area and magnetic flux density. The torque is defined by these three parameters. So in this video we discuss about the force between two conductors and force between two current loop and torque on the closed circuit, right? Thank you. Welcome viewers. In this video we'll see the definition of current and current density. First we'll see the current. So the current is defined as flow of charges per second. That is nothing but I equal to minus dq by dt. Rate of flow of charge per unit second. dq by dt is nothing but the current. Current flow is defined as the flow of charges, right? So this negative sign indicates the direction of conventional current is opposite to the electron current, right? That is indicated by this negative sign. So I equal to minus dq divided by dt. Rate of change of charges is nothing but a current. Now we'll see the current density. What is current density? Normally the current density refers either length, area or volume. Here we are referring the area, right? So why we are going for current density? Suppose if a steady current is passing through a conductor, the current density is uniform if conductor has uniform cross section, right? If a steady current is flowing through a conductor, if the conductor cross section is uniform, then the current density also uniform, right? Suppose if the current density will be different at different points, if the cross section is non-uniform, if the conductor cross section is not uniform, then current density also not uniform. It will differ from point to point, right? So based on that, so we can define current density. Current density is defined as the current flowing per unit area when the area is held normal to the flow of charges, right? So if the cross sectional area is uniform, current density also uniform. If the cross section area of a conductor is not uniform, the current density will different, right? So based on that, it is defined as current flowing per unit area. We are assuming that area is held normal to the flow of the charges, right? We'll see the definition. So current density J equal to di divided by ds, right? Current density J equal to di divided by ds. Current per unit area, right? Cross multiply these two, so that dI equal to J into ds, right? dI equal to current density into ds. By integrating on both sides, we'll get I equal to integral J dot ds. Is surface integral, double integral, right? So the current expressed in terms of current density as I equal to surface integral J dot ds. Now we'll see the conduction current. What is mean by conduction current? So this conduction current is nothing but normal current flowing through any conductor is the conduction current. It is the current flowing through a conductor whose resistance is R, right? The current what we are normally referring is a conduction current. It is flowing through a conductor with resistance R. Suppose if the potential V is applied across the conductor, then the conduction current IC equal to V divided by R, right? The potential V is applied across the conductor, the resistance of the conductor is R, so that the conduction current IC equal to V divided by R, right? So the conduction current is the normal current what we are referring flowing through the conductor with resistance R with applied voltage V. From this, the resistance of the conductor is given by, I will take this equation number 1. The resistance of the conductor is R equal to rho L by A, resistivity. In terms of resistivity, R can be replaced as rho L by A. This rho is resistivity. L is the length of the conductor, A is the area of the conductor. So while going into conductivity of the material, conductivity sigma is nothing but 1 by rho. Both are inversely proportional, conductivity and resistivity, right? So based on this R can be written as R equal to L by A. This rho is now replaced as 1 by sigma, right? This is not a rho, this is sigma. Now R can be expressed as L divided by sigma A, right? Now we can replace this R with this value. Similarly, the V. If E is the potential, E is the electric field intensity in a conductor, the potential V is given as V equal to E dot L. Normally the E equal to V by L, so that V equal to E into L, right? Now we got the expression for potential also in terms of electric field intensity, right? So the equation 1 is available here, IC equal to V by R, right? So the R we can represent it as L divided by sigma A, conductivity, right? The V represented as E into L in terms of electric field intensity. Now we can replace these two. So the equation 1 is nothing but IC equal to V divided by R. V is E into L, R is L by rho A, right? So that L got cancelled. So E into rho into A, right? So IC can, this is rho. Sigma, not a rho, is a sigma. E sigma A, right? So the conduction current is expressed in terms of electric field intensity, then conductivity and area of the conductor. IC equal to E sigma A. Now we'll see the displacement current. So in the displacement current, this current is nothing but current flowing through a capacitor when AC voltage is applied across the capacitor. So the conduction current is nothing but current flowing through any conductor with resistivity R and voltage V. The current flowing through the capacitor is named as displacement current, right? When AC voltage is applied, the current is flowing through the capacitor is nothing but displacement current. ID equal to dq divided by dt, right? So the displacement current can be expressed as dq divided by dt, right? But q equal to cv. This q is replaced as c into v, so that id equal to c into dv by dt, right? Now it is replaced as c dv by dt. From parallel plate capacitor, the C, the capacitor expression is epsilon A divided by D, right? A is nothing but area, D is the distance between the plate, this permittivity, right? So now we will replace this C with epsilon A by D, so that ID equal to epsilon A divided by D into dV by dt, right? Now we have one more expression is available, E equal to V by D. E equal to V by D, so that we'll replace this. So E equal to V by D, so this V by D, this dV by D is replaced as E, right? So that E equal to V by D. And one more expression is there, epsilon E. Epsilon E is nothing but displacement density D, right? So this epsilon E is now replaced as D, right? So we have epsilon C equal to epsilon A by D is replaced. After that, V by D is replaced by electric field intensity. Epsilon E is replaced by displacement density. So finally what we got, ID equal to A dd divided by dt, area into differentiation of displacement density, right? So the displacement current is nothing but current flowing through a capacitor, right? Now we'll see the convection current. So the name is given, convection means it is distinct from the conduction current, does not involve any conductors, and also it will not satisfy the Ohm's law, right? Convection current means it is completely different from conduction current, right? It will not, does not having any conductors, and also it will not applicable for Ohm's law, right? Then what is that convection current? It occurs when the current flows through a insulating medium such as liquid or vacuum, right? Without the conductor, it is flowing through a liquid or vacuum, then it is called a convection current. It does not flowing through any conductor, not satisfying the Ohm's law, right? So in this video we discuss the definition of current, then current density, conduction current, displacement current, and convection current, right? These topics are discussed in this video. Thank you all. Welcome viewers. In this video we'll see the definition of curl and the Stokes theorem, statement and proof. First we'll see the curl. The curl of a vector at any point is defined as the limit of the ratio of the integral of its cross product with outward drawn normal over a closed surface to the volume enclosed by the surface as volume tends to 0. So this is a definition given by the curl. So that curl is nothing but limit volume tends to 0 1 by v double integral surface integral n vector cross f vector into ds, right? So the curl of f is nothing but the volume is tends to 0, right? 1 divided by v n vector cross f vector into ds double integral, right? So that is the definition given here. The cross product of the outward drawn over a closed surface to the volume enclosed, so that is divided by v, right? So this is the expression for curl. This is the vector point function, and it is also referred as del vector del cross f vector, right? The curl expressed in another way is del cross f vector. So this del cross f vector is represented as I vector, j vector, k vector, first row. Second row is dou by dou x, dou by dou y, and dou by dou z. The third is fx, fy, and fz. Now we'll see the Stokes theorem. The Stokes theorem, first we'll see the statement. The line integral of a vector around a closed path. So this is the line integral f dot dl. The line integral of vector around a closed path is equal to the integral of normal components of its curl over any surface bounded by the closed path, right? So this is a double integral, surface integral of a curl of vector in the normal component of surface is nothing but the curl, right? So it is equal to line integral of vector around a closed path is equal to surface integral of curl in a normal surface. That is the statement given in the Stokes theorem, right? Now we'll see the proof of this Stokes theorem. So consider this segment is available, surface area S is available, right? It is split into so many small parts, this 1 2 3 4, like that n number of parts are available, right? So S is the surface area that is divided into so many segments, smaller elements. That is, in this diagram it is available 1 2 3 and 4, right? Now we'll see this. Consider a surface S, right? We consider the surface S. F vector is a field vector, right? We consider one field vector. From the definition of the curl, it is curl of F equal to limit S tends to 0, surface tends to 0, pi into F dot dl by S. So this is the definition from the curl, right? Now we consider one surface that is split into so many elements. F is the vector. Based on the vector, from definition of the curl of F is nothing but limit surface S tends to 0 by F dot dl divided by S. You take this equation number as 1. Now divide the area S into larger number of smaller elements 1 2 3 4 up to etc., right? So we are having the area S that is split into small elements, large number of small elements, right? In our diagram we shown 1 2 3 4 elements are available. So from this, based on the small elements, from the diagram we can write integral f dot dl equal to integral f dot dl1 plus integral f dot dl2, like that. 1 2 3 4, it will go like this, right? Now the big element is converted into smaller element, large number of smaller element, like 1 2, like that, dl1 dl2, like that, right? So from equation 1, f dot dl equal to curl of f dot s, right? That is the given from the equation 1. So by take the differentiate on both the side, so this integral become normal f dot dl. So while differentiating this side, what we got, curl of f equal to s become ds, right? So we are differentiating on both the side so that this expression become normal f dot dl. Already one integral is there, while differentiating it become normal. While differentiating this element, it become ds, right? So now we can replace f dot dl equal to curl of f into ds, right? This is for one element. Like that, while considering the n number of elements, integral f dot dl equal to curl of f dot ds1, curl of f dot ds2, like that. There are n number of surface available. So in general, we can write integral f dot dl equal to double integral curl of f dot n vector into ds, surface integral, right? So by now, first we consider the surface area, then split it into n numbers. From the n number of elements, we got this expression. So the Stokes theorem is proved. So in this video, we discuss about the definition of curl, Stokes theorem, statement followed by the proof. Thank you.